Good evening, everyone. I trust that you're all doing very well. Welcome to the second episode of Scientifically Speaking Season 6, a super cool online lecture series where we bring world renowned scientists straight to you, the curious minds of high school students and teachers. Over the past 5 seasons, we have taken you on a wild journey through some of the most fascinating topics in science. Everything from the mysteries of data science to the wonders of astronomy, the origins of life, the secrets behind the science of food, animal behavior, and even infectious diseases. And guess what? Season 6 is going to be even bigger and better. I am Kangna, your host for today's exciting session. I have a background in biology and completed my MSc at Ashoka University. And now I'm thrilled to be working with the Research and Development Office at Ashoka. Today, I'll be guiding you through what promises to be a fun, informative, and mind blowing session. So, without further ado, let me introduce our speaker for today. Our speaker today is someone truly inspiring. Please join me in welcoming Professor Sandeep Juneja. He's a professor of computer science and director of the Center for Data, Learning, and Decision Sciences at Ashoka University. Professor Juneja's research interests lie in applied probability, sequential learning, mathematical finance, Monte Carlo methods, and game theoretic analysis of cues. He has also been involved in epidemiological modeling as well as in the use of machine learning techniques for monsoon weather modeling in India. Today, Professor Sandeep is going to take us through the Monte Carlo method, a super powerful computational tool that has some fascinating applications, especially in understanding how diseases spread, with a special focus on COVID 19. So let's get started. If you have any burning questions during the talk, just drop them in the Q&A box on your Zoom screen and we'll tackle them at the end. A big warm welcome to you, Professor Sandeep. We're all super excited to hear from you and can't wait to learn something new today.
Thank you, Kangana. Very happy to be here. Shall we start?
Yes, Professor.
I'll just go ahead and share my screen. All right. Good evening, everyone. Such a pleasure to be addressing you. I can't see you, but I guess I'll be looking forward to your questions. So we are going to talk about Monte Carlo methods. Now you can see on your screen, the name actually comes from a Monte Carlo casino in Monaco. So let me go ahead and tell you a bit about it. So first, I'll just tell you what are Monte Carlo methods. So, you probably heard this problem before, that you want to find the value of pi by using random numbers. So now we all have an intuitive understanding of what random number means. Think of it as the capacity to be able to throw darts in a square uniformly, randomly, completely. So where the dart lands within the square is proportional to the area of the region that you're interested in. So now let's do this. So we throw a dart here. This is now a square with the circle embedded inside it, and the radius of circle is 1. So the length of a square is 2. All right. And then count the fraction of darts which are lying within the circle. Right? And you know that that fraction should be just the area of the circle divided by the area of the square. So that's pi by 4. I should have it here somewhere. So you do this maybe a few billion times, and that's the whole point. Monte Carlo methods really are about being able to generate randomness on the computers. So generating these billions or trillions of samples in milliseconds is quite cheap. It's quite easy to do. So you generate lots of these samples and find out the fraction of samples which lie on the fraction of samples which lie in the circle, basically. So that gives you an estimate for pi. So you get a pretty good number in a matter of milliseconds, pretty good estimate of this. Now, this idea of kind of generating randomness to compute quantities actually has a very interesting historical origin. It goes back to Comte Buffon, who was a French naturalist and a mathematician, and he created this experiment. these lines on the floor, basically grids on the floor, which are equally spaced, as you can. And now suppose you have needles which are equal to the spacing between the lines, right? And now you throw these needles randomly on the floor where you have these lines. The point is, where the needle center lands, there's no reason for it to be biased. So if you look between two lines, it has equal chance of being anywhere between the two lines. And the angle that it makes with the line is again uniformly random. There's no reason why, one angle would be preferred over the other. So it will be uniform. That's a very good assumption to make. So now once you made this assumption, it's an easy calculation to see what fraction of needles are actually going to intersect with the lines, what fraction will not. And that calculation is an easy one. I won't do it for you. Done in the 18th century. So this has a pretty old history. So this is using computers to generate randomness, but physically generating randomness. So this becomes another procedure for finding pi. So this is the history of Monte Carlo methods. We want to generate randomness, but generating randomness on computers again has a very colorful history. So, this was the time during the Manhattan Project near Los Alamos. Um, so Stanislaw Ulam is a physicist, a mathematical physicist, so a mathematician. And John von Neumann is John von Neumann. He should not need any introduction. If you don't know of him, he's a great person to search on the web and learn more about. People used to think of him as an alien because he was far too intelligent to be a human being. Um, he's a creator of many interesting mathematics. Quantum computing had major contributions, and Monte Carlo methods and more pure mathematical, more fundamental mathematics. So in any case, the story is as follows: that Ulam was recovering from an illness. So he was lying on a bed, he was playing with cards, and then he was there, and then he wondered what's the probability of seeing a particular realization of cards, the sequence of cards looking falling in a particular pattern. And it occurred to him, this was in 1940s, and shape. And again, John von Neumann had a key role to play in designing the architecture of computers. So it occurred to Stanislaus to do these calculations, that he doesn't have to do this mathematical calculation, wondering about permutations of cards that can come, finding out a favorable total number of ones and coming up with probability. It occurred to him that he can just use a computer to do these things for him, these samples. It also confirms one of my old theories that the best ideas come when you're lying around in a bed and not working too hard. So this kind of took off as a field. He discussed them with von Neumann, and they kind of, they were trying to solve for these massive integrals in their design of neutron bombs. And this was for doing calculations. Okay, so what is Monte Carlo simulations? Let me just, basically it's a tool to compute, for the most part, expectations or integrals. You don't need to know these things. Expectations, we have an idea, it means some kind of a mean. So let's consider this particular example to kind of narrow down the idea. So suppose we are going to conduct 5 coin tosses. If you see 3 consecutive heads occurring anywhere during those 5 coin tosses, you will win 500 rupees, right? If that does not happen, you will lose 100 rupees. Now, what's the problem that you will see? Do is you can enumerate all possible ways in which you can see 5 coin tosses, find the ones which are favorable over the total numbers, and that gives you the probability. So that's one way of doing it. That's through analysis. But analysis becomes hard very quickly. So how Monte Carlo will work is as follows. It will not solve the problem mathematically. What it will do is it will just flip the coins many, many times for you. So by actually flipping
Sandeep,
coins.
sorry to interrupt. Your voice is breaking in between. Would it be possible for you to maybe turn off your video? That will sort of ensure that we can hear you properly.
Oh, that'd be great. Sure. Just give me 1 second now.
Sure.
Let me see how to do that. I think I'll probably stop sharing for a moment. Is that okay now?
Yes. Yes.
Okay, so
Thank
let
you.
me go ahead. Let me go ahead and then. All right. So were people with me on this slide, Kangna?
Yes. Yes.
Yeah. So the point is, we want to find this probability of seeing, three consecutive heads in 5 tosses, and we'll use the computer to flip the coins for us. And computer can flip these coins extremely quickly. And then what we'll do is we'll conduct statistical analysis. So computer is basically generating data for us. We see all these samples, and then through statistics, we draw the conclusions. Not through analysis, but through statistics. So that's the key idea of Monte Carlo simulation. You don't solve the problem, you run the problem. You run the code. So for example, in the first trial, we saw T, 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 and then H, right? We saw 4 tails. So then in this case, we lost. We didn't see 3 heads consecutively, so we lost 100 rupees. In the second trial, let's say you did see 3 heads, T, H, 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 T, and you gain 500 rupees. You can see in this 10 trials, you won a few times, 3 times, and then you lost 7 times. So you can compute statistically. So you have 10 samples here. Now, maybe, but with these 10 samples, the average reward you earn was 80. And the standard deviation, standard deviation, it's a measure of kind of, we won't go into the technical details, but that turns out to be 289 in this setting. So it's large, you need more samples. If I give more samples, the overall sample standard deviation is going to come down. So law of statistics may be used to draw conclusions, and computers can generate thousands of such scenarios in a few milliseconds. Not thousands, actually millions. All right, so how do we do statistics? So let me just tell you all some key ideas in statistics. I mean, you're in the 11th and 12th. You've seen some of this already in your probability discussions, but let me just narrow them down for you. So, this seeing 3 heads in 5 coin tosses, you could do it mathematically, right? You know that each configuration has probability 1 upon 2 to the power 5. You'll find the favorable configurations, you'll get the answer. That would be probabilistically computing. And then, in favorable combination, you get a reward of 500. So 500 times probability of winning and minus 100 times probability of losing. That gives you the expected amount that you win of X. But statistics is going to generate samples of winning and losses. So it will generate samples X1, X2, and so on till Xn. And then this sample average that you see just from this statistical data that you've generated, law of large numbers says that the sample average is going to get closer and closer to E of X, expected value of X, that you computed exactly using mathematics. So what that means is, in many practical settings, the right-hand side is difficult to compute through analysis, but the left-hand side is much easier to do. So left-hand side then gives you a very good proxy for E of X. So that's the big idea of Monte Carlo methods. All right, so this is the key observation in Monte Carlo simulation. Now, the question is, okay, how good is this sample average? If I n sample, I got this X bar n, well, maybe it's maybe. So how good is it? And how many samples should I take so that I'm happy with what I've seen? For that, we require another big statistics, the so-called central limit. Again, I won't go into the details of it, but the big idea is that, X bar n, the sample average is converging to expected value of X. Each of these xi's, they have the same expected value. So this together difference is going to 0, but the question is how fast is it going to 0? And the way to answer this question is that you multiply it by something which is going to infinity. Turns out that square root of n is the right thing to multiply it to. So square root of n is going to infinity as number of samples n go to infinity. Sigma x is a standard deviation. It's just a normalization constant. It's just a number here. But this is going to infinity. This is going to 0. Together, the limit theorem tells you that they look like they have a probability distribution, which is normally distributed with mean 0 and variance 1. You've probably seen. It describes basically this left-hand side random variable distribution. What that means is if I were to generate samples of left-hand side independently, and it will look like a bell-shaped curve. A lot of readings will be very close to 0. Some will be on the slightly further away. Is my voice all right, Kangna?
It's breaking sometimes in the middle, Professor, but it's better than before.
Oh, that's too bad. I didn't realize the internet connection is not so good here. Okay, just let me know when to stop and maybe I can wait when the things go badly.
Sure, sure.
Okay, now, in more general settings, suppose I want to evaluate this f of x and g of x is a probability density function. So what that means is that g of x assigns probabilities to each x. It's basically a function which is non-negative and the area under it is, or volume under it, is equal to 1. I'm looking now at the space, which is, I'm looking at the intervals be very large. T can be thousands, hundreds of thousands, so on and so forth. That's the strength of Monte Carlo. You massive dimensional space, Monte Carlo knows where to throw points. So it usually does a pretty good job of estimating these things, even in very large spaces, while other numerical methods suffer from curse of dimensionality. So Monte methods don't suffer from curse of dimensionality. So that's the beauty of it. So if I want to estimate this alpha term, this integral that you're seeing here, what I will do is using g of x, I'll generate samples x1, x2, xn. These are again in this hypercube in d dimensions using g. And then with these samples, I'll compute the sample average, alpha hat. And by law of large numbers, as we discussed, this alpha hat will converge to this alpha, the integral that we are interested in. And these are the kind of problems which had motivated Monte Carlo method to begin with, computing large dimension integrals. All right, once we've done this, central limit theorem will tell you that this alpha hat actually looks like alpha with a small deviation around it. Deviation is given by sigma, which is a standard deviation. It's a constant number upon square root of n. It's the number of samples. So this is becoming smaller and smaller. And this is normal distribution with mean 0 and variance 1. This picture right here. This mu here is 0 and sigma is 1. So, 68.2% chance that you remain between -1 and 1, this quantity here. I think 95% chance that you remain between -2 and 2. So that's the kind of characteristic this number has. Very likely it will remain between -2 and 2. And then, this quantity together will be quite small for large n, and your alpha hat will look like alpha. So this is how statistics works. You can do precise estimation of alpha in this manner. All right. So let's carry on. But big point I just want to make here is that the rate of convergence, how quickly alpha hat is converging to alpha, given the standard deviation sigma, which is a constant, it just depends upon 1 upon root 10. It doesn't depend on the dimension of the problem. The hypercube can be very massive. It does makes no difference. Monte Carlo method is throwing points just at the right places where information is important. So it's gathering the information for you very efficiently. So that's the beauty of this method. This is just illustrating the central limit theorem at work. So, what I'm saying here is this, this green curve here is a probability distribution. So this is x-axis, and this is probability density function. Again, probability density functions are non-negative functions whose area under which is equal to 1. So this is what's called exponential probability density function. Area, it's non-negative, area under it's 1. If I want to find the probability of an exponentially distributed random variable lying between 0.5 and 1.5, I just go ahead and compute the area between 0.5 and 1.5. So it's basically giving me a prescription, a way of measuring probability. So if a exponentially random variable, this will tell me how it takes different values. Now, this is one random variable. Central limit theorem tells you that no matter what the random variable you have, if you sum independent copies of it, and you take large number of them, then the average begins to look like it has a Gaussian distribution. It's a very powerful result. It says that there's a distribution in invariance. Whether I start with this density function or any other density function, pretty much, if I sum many random variables, take their average, the average looks like it has a Gaussian distribution. And let's see that in play here. So this density function, if one random variable has it, I take 3 such independent copies of a random variable, divide by 3, I get this function here. This is a new probability density function, average of 3 samples. Mean is 1, standard deviation now is 1 upon root 3. So it's already looking like a bell curve. And then when I take 30 samples, it's very much like a bell curve. It's indistinguishable from a bell curve. That's why in statistics, they say that 30 samples typically are enough. You can use Gaussian distribution when you see 30 samples. And this is when you take 100 samples. What you're also seeing is that these curves look like bell curves, but they're also becoming more peaked. So the more samples you take, the more certainty you have in the sample average being close to the true mean value. So that's the idea here. Let me just say a few things. There are other methods for finding areas. So what I showed you was, I was finding an integral of f of x in one dimension. That's just finding area under the function f. So you can imagine the function f being this blue curve here. I want to find the area between a and b. Now you've seen that if you want to find area under the curve, there are these trapezoidal methods. You can draw rectangles and you can make trapezoids and you can use the areas there. And if you do a really fine job, you get a very good idea what the area is. If it does the calculation, you find that the error in this trapezoidal method is of the order of n raised to the power -2, where n is the number of samples you generate. And if the dimensions are d, it becomes n raised to the power -2 upon d. So what that means is that if d is million, then this is extremely slow. There's so many points you're going to throw in dimensions and do this trapezoidal method that's going to behave very poorly. So this is called the curse of dimensionality. All these methods which compute areas using more of these kind of rectangular or trapezoidal kind of methods are going to suffer from the fact that they'll have too many points in the space. A lot of places where you don't need those points. While Monte Carlo just has the convergence rate of 1 upon square root of n, so much, much faster. So that's a take-home message, that just by throwing points at random, you can estimate things much faster in large dimensional space. Okay, now I'll quickly tell you how we generate uniform random numbers. I started off by showing you a square, and I was throwing points at random. And I said to you that the computer can generate those points very, very quickly. So how does the computer actually generate them? And the real secret is that computer does not generate random points at all. It generates a deterministic sequence which just looks like it's random. We've done statistical tests of all sorts. We've chosen these numbers in such a manner that they satisfy all statistical tests of randomness. So you can't distinguish them from random numbers, but actually they're just a deterministic sequence. So we'll discuss this. By this random numbers, I mean uniform random numbers between 0 and 1. So numbers which lie between 0 and 1, but their chance of lying in any interval is just proportional to the length of the interval. Now, those turn out to be building blocks. Once you can generate those numbers accurately, you can use them to sample from any arbitrary probability distribution. So these are two steps. I'll quickly tell you what the underlying ideas are. Just good for you to know if you've not seen this before. So generating uniform pseudo-random numbers, pseudo because they're not really random. So we want to generate a sequence of numbers u1, u2, and so on, so that each ui is uniformly distributed between 0 and 1, right? So it's like rolling a needle on a wheel whose circumference is of length 1. So the chance of it lying in any interval, there's no reason why that should not be true. And they should be independent. So if I tell you one draw took some value 0.33, it should make no difference whatsoever to what the next draw is going to be. So that's the kind of properties we are looking for. We want the computer to generate this, to kind of roll this needle on this wheel for us many, many times. In practice, deterministic sequences are generated that appear to satisfy above two properties. And what's done typically is what's called this, a linear congruential generator. So you choose this number m, which is very large, 2 to the power 20,000, you have numbers of that sort. You choose some number a, which again is large, but it's very well chosen. You start with x0 as some initial seed between 0 and m. So, and then you multiply x0 with a, you get a massive number. You take the number modulo m, so then you get a number between 0 and m. And that becomes xi plus 1. Now just not able to get rid of this thing. In any case, what's hidden behind this is that each xi plus 1 that you generate, you divide by m, and that gives you a uniform number. Now you feed that xi plus 1 again in the above equation, multiplied by a, take modulo m. Like multiplied by a is like you're throwing, you're taking xi and rolling it along a wheel. And it means on that, when it goes round and round, that's divided by m, and that gives you the next number. So that's the broad idea. Now, choose M. How do we choose A? People have spent a lot of sweat and blood doing these things very empirically. They've done all kinds of massive tests, uniform numbers. You throw them in 10 dimensions, they should fall nicely in a hypercube in 10 dimensions or in 20 dimensions. If you draw their sequences, they're increasing and decreasing the way independent numbers should behave. So you test for all these things and you choose these numbers which satisfy all these properties. So that's the broad idea here. Now, once we have this capacity, this technology of generating uniform numbers, we can actually generate numbers from any probability distribution. So suppose I want to generate from a probability distribution whose distribution function is f of x here. So f of x for random variable x, it's just that the probability that random variable x is less than or equal to some small x. It's this function. So you can see that this function here is going to be, say a non-negative number, it's going to be 0 when x is 0 because random variable will not take negative value. And when x becomes plus infinity, this will be 1. And this f of x will be non-decreasing. As small x increasing, this probability is only going to increase. So it's a sum curve which starts at 0 and goes to 1 as x goes to infinity. So it's a curve like this. And you want to generate samples from a distribution from this function, from a random variable whose distribution function is f of x. So how do we do this? Let me give you a very simple idea. Suppose I want to suppose my x is a random variable which takes 3 values, 1, 2, and 3, each with probability 1 by 3. So I just want to generate samples 1, 2, and 3, which are equally likely. Now I have this technology with me, so I can generate uniform numbers between 0 and 1. That I have already. I know how to do that. So what I'll do is I draw this function f of x, for this random variable. It's 0 up till 1. And then this distribution function becomes 1 by 3 between 1 and 2. It becomes 2 by 3 between 2 and 3. And then it becomes 1. So I've just plotted this function, f of x. And now I'll generate a uniform 0, 1 variable, which I know how to. Suppose it lands here between 1 by 3 and 2 by 3. I simply draw a horizontal line here and drop it. When it touches this function, I drop it down to x-axis. So I compute the inverse of the function f. In this case, it drops at 2. So the chance that I'll see 2 is exactly a chance that the uniform number will lie between 1 by 3 and 2 by 3. So it's actually 1 by 3 probability. Similarly, the chance that this algorithm is going to output, I generate a uniform number here, and it lies between 2 by 3 and 1 by 3. In that case, I'll output 3. There should be 3 here. That's also probability 1 by 3. Similarly, whenever this uniform number lies between 0 and 1 by 3, I'll output 1. So this becomes a procedure where I convert a uniform 0, 1 random variable into a random variable which takes value 1, 2, or 3 with the equal probability of 1 by 3. Now, this idea generalizes. This idea extends to a general function like this. So I just plot a CDF, whatever it may be, of the function that I'm interested in. I generate a uniform number 0 to 1. Whatever value I get, I draw a horizontal line and drop it vertically, basically compute the inverse of this function f. This f inverse of u has the correct distribution. So this curve is basically stretching the uniform random variable in different ways so that I can generate different numbers from the right distribution. So that's the algorithm basically. One can come up with a variety of other algorithms which are sometimes faster, which have some nice properties. It's a very fertile area of research. But this inverse transform method, which I've described to you, is extremely popular. Okay, now let me, in the interest of time, talk a little bit about COVID modeling using agent-based simulation. Kangna, how much time can I use?
Professor, we have 5 more minutes.
Oh, just give me maybe 5 to
Okay.
7, 8 more minutes. Yeah.
Sure.
Because this might be more fun from reader's point of view.
Sure.
I should now, let's see, where do I go? I have to view, enter full screen. It's not giving me the option now to. Why am I not? Slideshow, there we go. Yeah, there we go. All right, so I'll describe, this is something we had done during the COVID time. This was few of us scientists in TIFR, and we had joined efforts with few of our colleagues at ISC Bangalore. So we created a city simulator, but we applied it, largely to Mumbai city. So it has 30 million agents. The idea was to create a replica of Mumbai city in the computer, a synthetic city which represents Mumbai in aspects which are important for COVID modeling. So what that means is that we'll have kind of coordinates of the whole city. We'll know where the slums are, where the non-slums are. We'll know how the population is distributed across Mumbai. And this information was broadly available. And we have an idea of how many people are living in each region. So we'll generate synthetic houses all across Mumbai to match our information about houses in Mumbai. We have census data. So we kind of use that to do this. So we develop houses, we populate it with people at the right age group from what our understanding of what the age population distribution in Mumbai is. Again, in slums as well as non-slums, we have an idea of where people go to work, how much time they spend in trains, etc., etc. So all of these things we recreate on the computer. So we create 13 million people, we geographically locate them, we give them a home, a family, a workplace, a travel in time, etc. And then, so once we've done that, once we created this synthetic city, so let me again say this. So demographics, employment, geospatial data for each locality, slums, etc., age, household, workplace, school size distribution, origin destination matrix for commute patterns, details of transport usage, and later on, are people vaccinated? How often are they? How frequently are people getting vaccinated? If there's a variant in the system, what's the status of the variant? So all of these things, all these details, one can model. So this is how the simulation is going to work. See, what I've told you so far is that we have a technology of generating samples from any probability distribution. So that's kind of where we are so far. We know now how we can use computer to give us samples of this. Now, how do we use that to kind of tame the uncertainty in modeling disease spread, in particular in modeling COVID spread? So let's see. So we create this synthetic city on the computer, and then we seed the city with initial infections at time 0. So we did some calculations and estimated that about 100 people were infected on February 14th or February 13th in 2020. So randomly, we look at non-slum areas and we select 100 people and we say that they are infected. So now these guys are tagged as infected. Now we'll observe the system every so often. In our case, we did this every 6 hours. And we'll look at each and every one of the 13 million people. So we'll look at a person and we'll say, okay, let's go to your home. We'll look at people inside that person's home and see if somebody is infected. So mind you, total 100 people are infected already. Then we'll go to this person's school if the person goes to school, or workplace if the person goes to workplace, or community. Community is defined in a particular manner. Community means going to bazaar, shops, etc., all that kind of stuff. So you go to all these places and see how many people are infected on those places. And then you have some assumptions about, if you go to a community and there are 5 people who are infected, what's the chance that you will get infected? What's the rate at which they'll infect you? So you compute these rates. Lambda CN, more the rate, more the chance you'll get accepted. Lambda workplace N, lambda school N, lambda home N. You compute this lambda, and then you flip a coin with some probability. So this is where Monte Carlo comes in. You flip a coin and decide whether this person that you've tagged right now, it gets infected or not. And you did this for all the 13 million people. So now you know that you started with 100 people. How many more have gotten infected? Now, once some people have got infected, what happens is first they just get exposed to the disease. They're not immediately becoming symptomatic. They're just exposed to it, and they may not even be transmitting very much at this stage. Actually, this transmission depends on how long they've been infected. So you update their disease state. And then, when a person is infected, we have a probability model for how long and how the disease will kind of progress in that person. I'll talk about it in a moment. So that happens now independently of everything else. But the person is infected, so after a while it starts infecting other people. So that in that manner, they start infecting other people in the sense that the next time period, people in their homes, in their schools, in their workplaces are now likely to be infected by these people as well. So this is how the process continues. So let me give you an idea of how the disease progresses. So suppose a coin was flipped and a person got infected. Then the person will stay exposed for an average of about 4.5 days. This is from the study that was done in December in China, where the COVID had started. So they had computed these numbers, and they had a probability distribution as well. So we don't just say that the person will be infected for 4.5 days. We sample from a probability distribution, and that's where Monte Carlo simulation comes in. And that tells us that this particular person will be exposed for so many days. And then with some probability, this person will become infectious. Well, first it'll become, I guess, it will become infectious, but it will be pre-symptomatic. And then with some probability, this pre-symptomatic person will actually become symptomatic. And the symptomatic person with some probability will get hospitalized, and this will happen on an average after 5 days. Again, there's a probability distribution to fit the data that we've seen. A person who's hospitalized will stay on an average 8 days, but again, a probability distribution. And all of these are now age dependent. So if the person was elderly, then some of these probabilities go up. Hospitalized person with some probability will become critical, with some probability they'll recover, so on and so forth. And then with some probability, the critical person may not survive. So these are all the data that we've seen, we fitted probability distributions to get a realistic idea of how the disease progresses in any person who's exposed and how long they're symptomatic, when there's, well, how long they're infectious. When they're infectious, they're infecting other people. Okay, so you have probabilities such as this. I'm just telling you to give you an idea that, if you're between 40 to 49 age, then given that you're symptomatic, probability that you get hospitalized is about 5% probability. Given that you're hospitalized, probability that you become critical is 6.3% approximately. Given that you're critical, that you don't survive, it's about half a chance. So these were the estimations that were done based on data, and now we use that in our Monte Carlo tool. All right, and then, when you have lockdown, case isolation, home quarantine, all that means is, suppose you have a lockdown, then if you're with somebody who's infected in the home, you stay longer in the home, your rate of getting infected from that person is going to become larger. You probably won't go to the community that much, so your rate of getting infected from the community will come down. You probably will stop going to work, so your rate of getting infected from work will come down. So in that sense, how your mobility changes based upon the restrictions placed upon you by the government, etc., can be modeled just by changing the rates at which you get infected. So with this, now you can develop these projections. So let me end, say a few things very quickly and before I end. So this is our report for Mumbai in October 2020. So, in Mumbai, the disease started in February. It was always good to report fatalities because fatalities are more accurate numbers than case numbers. People don't go and get reported if they have symptoms often. So fatalities saw a steep rise. You can see here. There's a steep rise in fatalities in Mumbai numbers. And the peak happened, I guess, between May and June. And thereafter, there was some decline. And then again, a peak happened here. This was because of there was Ganpati festival, and suddenly people started coming out in the streets. So there was another increase. And thereafter, the numbers came down. We had learned a lot. So when we saw this steep increase, we tried to match it in our simulation model. And we figured out kind of, what are the rates of infection at home, in communities, in school, in workplaces, etc. We chose them, based upon our understanding of the data and to match the slope exactly. So this was a fitting exercise, and there were restrictions imposed, and we kind of, saw that these restrictions were more or less kind of explaining all this. And again, we tailored our model to match the fatality data. This is where we kind of saw this increase in fatalities, and we said, okay, what this really means is that people have suddenly become more lax. They are traveling around more. They are not compliant as much as they used to be. They go to communities much more often. So we understood this. Once we understood all of this thing, we could model, okay, how will the crowds behave in Diwali, in Christmas, and all the other holidays. So we could model all these things. We could also model that if schools were open, how would COVID spread in that setting? So these are the curves that we had developed. This blue curve, this green curve is saying that if you open up the economy, the trains on November 1st, how the disease will spread, what will you see? On the other hand, if you open up on January 1st, then you'll see this orange curve. So this was a forecast we had made in end of October. I won't go into many details, but the intent was to be, we knew a fair amount at that time, so we were trying to be accurate. And this is exactly what had happened. So 4 months after that, from October, end October to January end, because what happened was Mumbai actually opened up on February 1st. That's when the trains opened up, offices opened up. So till February 1st, actually, you see, our model actually does a pretty good job of predicting how fatalities behave. It's a little underestimation, but it seemed okay because, as people see that the disease is coming down, they change their behavior. So once you account for that, actually, our model, this would have done a pretty good job. But I'm not showing you anything further because what happened after this was the Delta wave came, which was completely surprising. And all of our projections here went topsy-turvy because nobody anticipated that such a variant could occur. And then we had to do a lot of other things. But let me end with that for now. This is just to tell you that Monte Carlo tool is very powerful. It kind of models uncertainty, and it becomes a decision-making tool, when used with the judicious judgment. Thank you very much.
Thank you, Professor, for such a knowledgeable and insightful session. We can now start with the Q&A round. Starting with the first question, how are computers changing the way we study diseases?
Well, this is exactly a very nice way to illustrate that, right? And this is for infectious diseases, because you want to understand how infectious diseases spread. So now you can build a kind of a micro agent-based model at a very kind of detailed level, and gives a very good idea of how diseases are going to spread. So this is used, for example, for dengue modeling right now. I think even for mpox, people have started using these kinds of models. Um, so computers play a major role in doing a pretty good job of how the disease is going to spread. Now, I should mention to you, it's a tricky issue because, this randomness actually makes disease spread very a complex problem. So for Mumbai, we could do a good job because Mumbai is very crowded and it's on a and there are lots of people. So once the disease takes off, it has a lot of certainty. The uncertainty kind of averages out, and we have a fair idea of how the disease is going to spread. But in regions which are less crowded, more spread out, the disease evolution is a very stochastic, very probabilistic process. So with some probability, mpox will flare up, with some probability, it will not. So it's a more complicated evolution, and computers make this clear to us, how the disease spreads. They give us a much better idea of the uncertainties involved. So it's a very good tool. All the earlier tools which we had earlier would not be able to do this kind of detailed level understanding, probabilistic understanding of disease spread.
Okay. Thank you, Professor. The next question is, there is still a margin of error, although it may decrease with more samples, but does it ever completely disappear? If not, can we trust this method enough to make decisions of high or fatal importance?
Right, right. So it's a very good question that, all these models and fancy models one can design, but can one rely on them? Do they actually help us make accurate decisions? So many things are important. First is, these models are as good as the inputs that you give to them. We are saying that we know what the disease rates are, how disease spreads at home, at workplace, and the sizes of home population. We're saying that if a person has a certain age, then that's the rate of disease spread. All these are numbers that we have really only a very approximate idea of. And, when the lockdowns happen, how much mobility is reduced. So these things are extremely tricky to get hold of. So one always has to be skeptical of these models. There's lots of model uncertainty. It's a real world setting. It's not like particles which are following simple physics laws, where we have a very good idea of how they're going to behave. This is a real world setting. People are very unpredictable. So one has to be very skeptical of all the modeling assumptions we make. So yeah, so in that sense, one can never rely completely on the outputs that come in, but you have an intelligent understanding of what the model is saying. And what these simulation models also allow you to do is a lot of what if analysis. What if mobility was not this, but so much more? What if disease was not infectious at rate X, but maybe 5X? All of these what if scenarios you can do. So you have a better sense of what to be careful about, what to watch out for, what interventions work, what don't. So in that sense, these are kind of very useful decision-making tools, but they should certainly never be used blindly. All kinds of wrong things happen that way. That's true for all mathematical modeling, because all mathematical modeling lies on making simplifying assumptions on how the world behaves. And those assumptions one has to be very careful about.
Yeah, thank you, Professor. Moving on, how does a linear congruential generator ensure pseudo-random numbers are uniformly distributed between 0 and 1?
Like I mentioned, through a lot of sweat and blood and testing. So people have, spent years testing different parameters for linear congruential generators, and they choose the ones which match the statistical test the uniform numbers satisfy. So uniform numbers, if they're truly independent, have certain properties, right? If I throw them, if I take a vector of, say, 100 of these numbers, one after the other, and I take lots of those numbers and I throw them in a 100-dimensional hypercube, they should space. They should not line up in some areas and not in the other areas. So you choose your linear congruential number to have those properties. If I give you uniform independent numbers, and if I look at the number of sequence, if I plot the sequences where U1 is smaller than U2, is smaller than U3, is smaller than U4, these kinds of subsequences where the uniform numbers are increasing or they're decreasing. So if they're truly independent, they will have certain statistical properties. They will have certain distributions that they satisfy. Now, the numbers that you're generating should also satisfy those properties. If you run your hypothesis testing, you should not be able to conclude that these numbers don't look uniform. So it's a very empirical exercise in a way. There are some theoretical things that you can do. You can ensure that your linear congruential number is theoretically not going to get bogged down in certain region. Because, if you look at the formula of the linear congruential number, once a number repeats, it just cycles all over again. If I go back to the formula here, let's see if you can see my screen. Sorry, if you can see my screen here. So once an xi plus 1 is equal to x1, then xi plus 2 will be equal to x2 and so on and so forth. So these numbers will repeat themselves. So you can theoretically at least ensure that you've chosen numbers in such a manner that they don't repeat for a very long time. And then with that and with some empirics, you kind of choose good numbers.
Okay. Someone is asking that they notice that f of x and an inverse of f of x plotted look like a sigmoid. The first derivative would be bell-shaped maybe. Is that connected to why the inverse transformation is used?
No. I mean, you can give me any curve here, f of x. All I need is it starts at 0 and ends at 1 and it's non-decreasing. So every such an f will correspond to some random variable. And every such f, this method will work. So this is just, just to illustrate an example. But yeah, it can't go beyond 1 because this probability here cannot exceed 1. So in that sense, it has to lie between 0 and 1. But other than that, the shapes are arbitrary.
Thank you, Professor. The next question is, what is the best known method to generate a uniform random variable in the literature better than linear congruential generator?
Yeah, you can do a quick search on this. There are these Mersenne twisters, which are pretty good now. They use a more complicated form of this kind of, sequential sampling, sequential property of linear congruential generator where xi plus 1 is derived from xi. And they have a larger period before they repeat, and they're shown to have better properties of randomness. So Mersenne twister. Now, there are other methods which actually use, kind of physical randomness. They inbuild that inside those numbers to just ensure that they become less predictable. But those numbers, you can't really generate many very quickly. I mean, that's the other thing, what we are looking for is a quick method, an accurate method, and reproducible methods. So if it's reproducible, then you can test again. If there's a bug in the code, you can check if it's because of randomness or if it's because of something else. So there are all these properties one is looking for. And if you're going to use physical randomness as some methods do, then you have to store millions, billions of numbers, and that's very inefficient. Yeah, but this is an easy topic. You can kind of do a search quickly and get an idea of what the algorithms are.
Thank you, Professor. How can the Monte Carlo method be applied to model the spread and control of mpox, particularly in scenarios where there is significant uncertainty in the data or the parameters affecting the disease transmission?
So I just repeat the question again. I missed a key word in that.
I'll repeat the question. How can the Monte Carlo method be applied to model the spread and control of mpox?
What does that mean, mpox?
Mpox is the monkeypox.
Oh, I see. Mpox. Yeah. I can't help you there. Sorry, I've not been following the disease mpox. I'd imagine it would be very similar to COVID modeling in the sense that you will get an idea of how fast the disease is spreading, what's the chance that it can spread. And if you kind of do some careful interventions, for example, for COVID, this was the case that if you were to screen people coming from airplanes, somehow reducing the amount of population that comes in, then you can significantly slow down the disease. I think Mpox is probably not as infectious as COVID, but otherwise it's important to slow things down so that you have time to plan your actions, maybe come up with vaccines, so on and so forth. So in these kinds of ways, generally these computer simulations, mathematical models are useful. They help you plan better. They basically help you evaluate all the different interventions which are available to you. Should you impose a lockdown? Should you have travel restrictions? Should you screen passengers? So on and so forth. And then you get an idea of how these things work. You can make the right decisions.
Okay. The next question is there room for evolution and growth in this model that could somehow actually predict every small detail and maybe even predict the future? Is that a possibility?
Well, so future is probabilistic in this. So, I mean, that's one thing to kind of accept, that even if you could predict the probability distribution of the future, you're not really predicting the future. So, I can predict the probability distribution of next 20 coin flips. Doesn't mean I'll know exactly what will happen on those coin flips. I mean, for that, you will need a more deterministic model where you're kind of modeling the wind speed, the force with which the dice are being hit, a lot more other details. But that you can probably do for coin flips, but you can't do for all the other uncertainty in the real life. Now, that's if you knew the probability distribution. So now your point is, can we, if we have better idea of the information on the ground, how disease are spreading, how people behave, all of these kinds of things, can we do a much better job? Certainly. But I should also tell you that, for most of these things, one doesn't need to do 100% accurate job. You just want to make good decisions. You want to know when to impose a lockdown, what kind of interventions are useful, uh, which population to give vaccines to, so on and so forth. So for many of these decisions, you don't have to be extremely accurate. You just have to make sure that you're not extremely inaccurate. You don't want to make terrible decisions. You don't want to miss out the elephant in the room, so to speak. So in that sense, yeah, there's always room to do a much better job. And that's desirable. But if you do a pretty good job, it goes a long way in making good decisions.
All right. Thank you, Professor. The next question is, can the Monte Carlo method be used alongside differential models like SIR or SIRV with quarantines to compute probabilities such as recovery or infection rates? Or is it more of an alternative to solving differential equations, replacing methods like Euler's?
It's a very nice question from somebody who's quite knowledgeable. So SIR kind of models are very simplistic models. So all population is homogeneous. They either get infected or they remain susceptible, or once they're infected, they recover at some point. These are extremely simple models. In simulation, we are trying to capture much more detailed characteristics of the population. So if you have a simple model, why do you need to combine it with a detailed model? That's one part of the story. I mean, nothing mathematically prevents you from combining partial differential equations wherever they are necessary, along with Monte Carlo simulation, wherever, use partial differential equations where they are working well and use Monte Carlo simulation where uncertainty is important. So technically, nothing prevents you from combining these things. But SIR kind of models are too simplistic. The way to think about these simulation models are that if in SIR model you start adding much more details, like age distribution, geographical, spatial information, etc., and then you have a partial differential equation with, say, like thousands of dimensions. And those partial differential equations you can't solve numerically. There's a curse of dimensionality. The only way you can solve them is through a Monte Carlo simulation model. So in some way, these simulation models that I've showed you are actually a tool for solving large partial differential equations. They're the only way you can solve a large SIR model. So at this point here, it's a very interesting point that, we use this randomness to solve a deterministic system because, the pictures I showed you, the evolution was more or less deterministic in a large city. But those deterministic systems, you couldn't have solved it any other way. Simulation was the only way to solve them.
Okay. The next question is, can we predict the incidence of crimes such as violence against women in India by the Monte Carlo method?
Um, all of these are kind of, functions of the inputs you give. So I don't think you'll get anything new from doing detailed mathematical modeling. The problem is elsewhere. If you have violence against women, the solutions are elsewhere, the problem is elsewhere. Mathematical modeling and these Monte Carlo methods, which are used to solve mathematical models, are a tool which probably have very little role right now to help you solve these problems. Yeah, so it's not clear to me. I mean, better surveillance, better cameras, better transfer of information would be very useful. That kind of technology has a role to play. But mathematical modeling, how that can help, it's not at all clear. It can just make you understand maybe, okay, this is how these incidents happening in different geographies, this is how they're evolving, this is how things are changing, and what does that mean? So they can help you with those statistics, which then need to be interpreted and making good decisions.
Okay. Thank you, Professor. We can now take just the last few questions. How do you see this method evolving in the future, particularly with the rise of new technologies like quantum computing?
Right. Well, quantum computing is still very far. It's still early stages for it. We can only solve some very specific problems. Uh, so let's put a hold on that one. It's not clear where quantum computing will be 10 years or 20 years from now. But the other technology which has taken off and which is transforming the world we live in, as you know, is machine learning. With all these large language models and all the developments in deep learning, the question then you can ask is, okay, how do these Monte Carlo simulation models sit along with these machine learning models? There, I think it's very interesting what may happen. Because as you can see, as you may have learned, that these large language models are trained by using all the data that there is on the internet. And people are building, enormous computational facilities to evaluate that data. A lot of money is being spent. Uh, Pretty soon, you'll run out of actual data to train these models. And then the issue would be, okay, how do we train them better? So that's where Monte Carlo simulation may have a role to play. It can artificially generate data because, Monte Carlo simulation can do a lot of what if analysis. Reality, the data you see is on the internet is, reality that was actually realized. But there are many things which you have not seen, a lot of counterfactuals. Those you can generate via simulation models. So you generate a lot of simulation data of what you've seen and what you might see in future and train your model to those things. So in that sense, Monte Carlo simulation models have a massive role to play in future. First, as compute continues to improve, we can do more things with Monte Carlo. As we get more data, we can better fit our mathematical models, have more accurate mathematical models. And secondly, these can actually be used to train your humongous machine learning models. Because, this simulation model, which I'm showing to you, they actually, after 2 years of COVID in 2021, when we were modeling for Omicron, running the model for 2 years was taking 13, 14 hours just for a single run. So computationally, it was prohibitive. So if instead we had trained a machine learning model using this data so that it could give some answers instantaneously, that would have been a hugely useful thing to have. So those are the kind of directions where you do see Monte Carlo simulation kind of playing a role in combining with emerging technologies.
Thank you so much, Professor. We'll take one last question. Can you provide some applications of the Monte Carlo method in areas other than scientific research?
Monte Carlo methods are used massively in finance. So, if you were to, I guess, for example, become a quant, or quant is a mathematical person on Wall Street, lots of strong engineering mathematical students, PhDs, are employed by Wall Street in the world of finance, where they're evaluating, okay, how does a large portfolio behave? Portfolio is, for example, a bank has given millions of loans. Loans can be of all sorts. Credit card companies give lots of loans. So you want to see, and all of these loans, etc., and all these stock prices and other financial securities, they have uncertainties attached to them. So one fits probability distributions to them, and now you want to evaluate some properties, like what's the probability that there'll be a large loss in this portfolio, so on and so forth. So Monte Carlo simulation is extremely useful there. Businesses generally, manufacturing businesses have supply chain models where they're kind of modeling how the product is being made, how it's going from one set of machinery to the other, how it distributes amongst customers, how the inventory behaves. All of these things, Monte Carlo simulation is used to get a good idea of how the system is behaving when we do all kinds of what if analysis. Because decision making gets complicated very quickly. So we make decisions based upon the few facts that we know. We don't need any mathematical modeling. But when millions of people are involved, then you need to make a mathematical model to get a better idea of how the processes are going to evolve. And mathematical models in real world, in businesses, and outside of science involve all kinds of uncertainties. You model them using probability distributions, and then simulation becomes useful in understanding the performance and optimizing the performance. You have to make decisions. So Monte Carlo simulation allows you to play with the space of decisions and find the best ones.
All right. Thank you, Professor. That was the last question. Thank you again for such an insightful session. We will now proceed with a few formal announcements. So you are welcome to log out at this point if you wish. Thank you once again.
Thank you so much. I'll log out now. Thank you.
Before we wrap up the session, we would really appreciate it if the audience could please take a minute to share your valuable feedback with us. The link to the feedback form is provided in the chat box. Please note that the recording of this session will be available on Ashoka's YouTube channel in case you would like to share it with your friends. The next episode of Scientifically Speaking Season 6 is scheduled for Tuesday, that is 10th September at 6 p.m. IST. The session will be delivered by Dr. Sushmita Saha, faculty member, Department of Physics, Ashoka University. The title of the talk is Magnificent Magnets, From Compass Needles to High-Tech Gadgets. In this talk, Professor Saha will discuss the fundamental principles of magnetism, exploring how magnets generate magnetic fields and their applications in everyday technology, from motors and data storage to medical imaging and advanced scientific research. I would also like to inform our audience that registrations for the undergraduate program starting next year, that is August 2025, are now open. I would encourage students to register soon and have access to personalized mentorship with our academic counselors, interactions with Ashoka students, and learn more about the campus life and receive guidance from Ashoka's holistic admissions process. For more information, you can write to us at ugapply@ashoka.edu.in. This brings us to the end of this session. Please take care and stay safe. Thank you for joining.